our book mostly talks about powers of 10 in the next chapter, in the third chapter. But to us, that's not nearly as important. You do have to work in powers of 10 back and forth, but more importantly, as always, is engineering notation. Okay. Wonder what that says behind there. Order of operations. This one always cracks me up. Whenever my daughter sees this, she goes, "What grade are these guys in? 7th grade, 6th grade, 5th grade, 4th grade?" Okay. The mnemonic, PEMDAS, or please excuse my dear Aunt Sally, parentheses, exponents, multiply, divide, and subtract is the order of operations. There will be a trick question on the final exam that is a PEMDAS problem. When you look at it, you go, well, that's just multiply and add and divide, subtract. Think trick question. If it looks too easy, it is. I'm not joking, there will be a question or two on PEMDAS, and it won't say this is a PEMDAS question. It will say, what is this? Evaluate this equation. And it comes out to a single number or a 2-digit number, something like that. And it's a trick question. It's a PEMDAS question. If you don't do it in the correct order, it'll come out with the wrong answer. If you just work left to right, it'll come out wrong. Okay? So that's your warning for the day. Oh, isn't that cute? Just love that. All right. Okay. Find the value of the expressions in parentheses, evaluated powers of 10. Do all multiplication, division in order from left to right. Do all addition and subtraction in order. So that's PEMDAS. I think you should remember that from the 3rd grade or thereabouts. Okay, the formula for the area of a circle is the area is equal to pi r squared. We use that a great deal in electrical work. You realize that, right? If we're looking at the volume that's available in a conduit, the area of the cross-sectional area of that conduit is an area, right? In square inches. We can figure that out. And we can't fill it, generally speaking, more than about 40%. So we need to figure out 40% of that area and then find the area of the wires, because they're round too, pi r squared again, find the area of those wires, add that together, and make sure that one is not more than 40% of the other. So, and then there's lots and lots of other places where it's used. It's just, that's one you might want to remember. Pi r squared is cross-sectional area of a circle, right? First, since D is 3 inches radius, we're giving an example here. We have a 3-inch radius, like a 3-inch conduit. So the diameter of the conduit is 3 inches, so the radius is 1.5 inches. And you want to find the area. Okay, 1.5 inches is the radius, 3.14 is still pi. Write out the formula, substitute the numbers, simplify the exponent first. So 1.5 squared is 2.25 times 3.14. Nice simple operation there. We're going to get 7.065 square inches. And so the cross-sectional area of a 3-inch conduit is over 7 square inches. But what's 40% of 7? A little under half. So we would have 2.8 square inches of area to put wire in. Okay, multiplying powers of 10. Once again, you probably remember some of this from 5th or 6th grade. But remember that exponents are easier to play around with than you realize. They make things, exponents make things simple to work with. Let's see. And you notice I changed these slides so that they were all, so that you could all simplify them into engineering notation. So this one right here would be the 345,000. That's 345K something. the 10 to the third something is 6.5 times 10 to the third, and so on and so on, dividing by powers of 10. The nice thing about this is that when you're working in powers, if you're dividing by a power, you can take that and put it above the line and put a minus behind it and use it as a power. So divided by 10 to the second becomes multiplied times 10 to the minus 2. And if you're multiplying it times another power, which we always are, then mostly they will either cancel out or just leave a power of 3 plus or minus kind of thing. So the engineering notation is a simplification device. It's going to make actually life a lot simpler for you. Multiplying times negative powers, multiply values by numbers expressed as 10 raised some negative power. We just subtract that from the positive power that we're multiplying times most of the time. Okay, this is talking about moving the decimal point back and forth, which you do have to do occasionally. So look this over again if you're not clear on how to move the decimal point. Again, divided by negative powers of 10. Nice and simple. 15 divided by 10 to the minus 2 is just like 15 times 10 to the second power. Okay. So it just moves above the line and becomes the opposite sign. Okay. Oh dear. Okay. What does that say here? Expressing numbers larger than 1,000, greater than 999, as a small number times a power of 10 using engineering notation, in other words. To express a large number as a smaller number times a power of 10, move the decimal point to the left as many places as desired. I'm going to multiply the number obtained by 10, power which is equal to the number of places you're going to move. Okay. 3,000 of something is 3 times 10 to the third, or 3 kilosomethings. 4,500 becomes 4.5 kilosomething. 770,000 is 770K. Then we have a bigger number. 8 times 10 to the 6th would be kilomega. 8 times 8 mega something, right? Nice and simple. And then we have 9 places. Oh, I failed to superscript the 9, sorry. That's not times 109, it's times 10 to the 9th power. 9.23 times 10 to the 9th. What is the 9th power? Kilo, mega, giga. So this would be 9.23 giga somethings, right? And then we have 10 to the 18th. Remember I said I'm not greedy, but I'd like to have 2 or 3 exadollars. Here we have 6.25 times 10 to the 18th. We know that's the number of electrons in a coulomb. Okay, now let's look at really small numbers now. And we're going to move the decimal place to the left to get rid of that really long string of zeros. Then multiply times the negative power of 10. For instance, at 0.005 is really 5 millisomethings, right? That's a simple one. If we go 0.00672, that's 6.72 times 10 to the minus 3, or 6.72 millisomethings. And we have 6 places. So 10 to the minus 6 is micro. So 7.58 micro somethings. Then we have 10 to the minus 9. Milli, micro, nano. So we would have 8.9 nano somethings. The handy part about multiplying, recording things in the way again. A to the 4 times A to the 5 is just A to the 4 plus 5. And if what's more common is, well, let me come to that in a minute. and we would have 8 to the 9th, 10 to the 5th. But what's more common now is, let me go back to A. What's more common in electrical work is you'll have A to the 4th and A to the minus 6. And in that case, where you've got a larger negative number and a positive 3, a negative 6 and a positive 3, you would have 10 to the minus 3rd left over, so it would be a millisomething, right? So if you have, now look at C, and I want you to realize that this is simplifying the math for you. If you look at this as 25K something times 4K something, you've got 25 times 10 to the 3rd times 4 times 10 to the 3rd. So if we just regroup these so we have the whole numbers together and the powers of 10 together, we now have a nice simple 25 times 4, which we all know is 100, and 10 times 3 times 10 to the 3rd, we have 10 to the 6th. So we have 100 times 10 to the 6th. Now we need to get rid of 2 more zeros, right? Well, we can't, because it's any number between 1 and 999 is okay. Anything above 999, 999, we need to go to a larger unit. Anything below 1, we need to go to a smaller unit. Okay. Now, 10 to the 8th. I think that's a typo. I think I have a typo. I can fix that later, but you know that's 100 times 10 to, oh, I see 10 to the 8th. We took the other 2 zeros out.
Yeah.
The book did that, not me. I can tell you that much right now. Okay. I still want to go back to this one. If we had 25 times 10 to the 3rd times 4 times 10 to the minus 6th, you can see that you would have 100 times 10 to the minus 3, right? So that'd be 0.1, right? 100 millisomethings. Okay. All right, so our 7,000 times 0.00. Now this is more an example of what we really do. We have 7 times 10 to the 3rd times 0.0091. In electrical engineering notation, we would make that 910 micro somethings, right? And so it'd be 10 to the minus 6th, so we had 910. But if you want to simplify it to just get the numbers, you have 7 times 10 to the 3rd times 9.1 times 10 to the minus 4th, and you can resolve that down to doing the simple multiplication of 7 times 9.1 is 63.7, and then resolve the powers. 10 to the 3rd times 10 to the minus 4th is 10 to the minus 1, right? Okay. And that all boils down to 63 times 10 to the minus 1. We're going to move the decimal place which way? One place to the left, so it becomes 6.37. Can you see how the engineering notation of the powers of 10 make things simpler to look at even when they're big numbers and really, really small numbers? And that's the whole purpose of engineering notation. Once again, it's the language of electrical work. Didn't even know I could move that. Also notice the same example, how simple the powers became. Okay. I think this says example. Oh, gee. Multiply 0.0005. We would call that 50 micro somethings times 20 times 20,000 times 1,500. Now I put them in different colors so that you realize that this is a certain kind of number. It's a small number. It's going to wind up being what? 50 millisomethings. 20 is going to be 20K, and 1,500 is going to be 1.5K, right? So now let's take that down and simplify it some more. And we can see that that becomes 5 times 10 to the minus 5th, 2 times 10 to the 4th, and 1.5 times 10 to the 3rd. And if we multiply very simply, what is it? 5 times 2 times 1.5. I can almost do that in my head, right? 5 times 2 is 10. 1.1 times 10 is going to be 15, right? So we have 15 times 10 to the minus 5, 4, and 3. And so that's going to be 2, right? 10 to the second power. So it's going to wind up being 1.5 times 10 to the third. Is that correct? 1.5 times 10 to the third. All right. I may have an error in it. I've got to look at that. Okay, division. Not sure I even left this in. All right. I guess I did. 10 to the 6th divided by 10 to the second. If we move 10 to the second, it's a division of. We move it up, it becomes 10 to the minus 2. And we can just add the exponents. 6 minus 2 is 4. 10 to the 4th. 4,000 divided by 10 to the second. In other words, 4,000 divided by 1,000. 4 times 10 to the third minus 2 would be 4 times 10. Gets a lot simpler, right? Okay, 35,000 divided by 0.005. You would look at that and freak out and go, oh, I can't figure that out. Then you realize, well, that's just 35 divided by 5, right? All right. Anyway, it becomes a really simple expression once you boil it down to just whole numbers and powers of 10. Anytime you have, now this will happen fairly often in electrical calculations where you have 10 to the third times 10 to the minus third, which is the same thing as divided by 10 to the third, and you get 10 to the 0, right? That's 1. So it nullifies itself out. So 10 to the third times 10 to the minus third, that's just 1. It drops out, in other words. Let's solve another expression, 0.0075 divided by 500. Sounds pretty complex, but we can make that 15, well, let's look at the next. Let's see, we're dividing 75 by 5 when we know that's 15. That's fairly simple. And then we have 10 to the 5th, 10 to the minus 5 times 10 to the minus 2nd, so 10 to the minus 7th. And 60 divided by 0.003 times 4,000 is equal to 60. You can see how using this makes things so much simpler to work with. I mean, this expression boils down to a simple number 5, but you never know that looking at that complicated looking thing, right? All right. So what kind of problem is this? Trick problem. It's a trick question, right? What kind of trick question is it? PEMDAS. So what do you have to do first? Inside the parentheses. So 8 minus 3 times 5. If you multiply 5 into the next thing, you're probably going to wind up with a wrong answer. Okay, this doesn't look very hard, right? That's actually fairly simple. I don't think you can screw that one up. Okay, minus 60 divided by 8. Trick question.
I have a question. How can number 1 be 1?
I don't know. It's from the book.
Oh, okay.
I left it in there just because I didn't want to play around with it. It's probably okay. That's 5 times 5, 25 plus 7. Because you're going to multiply before you add, right? So 5 times 5, 25 plus 7. I think they made a typo. It's not my typo this time.
Okay.
Okay? But yeah, I think they made a typo there. Okay. 835 divided by 10 to the third. Changing units of measurement. I used to have a whole long thing of, I'd give you furlongs and tell you that a furlong is 6 feet and tell you a number of feet and say, how many furlongs is it? First converts the value of the metric unit to a coefficient with a required power of 10. In other words, if you use a power of 10, it's going to make it easier to analyze almost anything. Substitute the engineering notation values whenever possible. Changing large units to small units. Let's have an example of that. 2 gigavolts, 2 volts. Okay, this is the exact opposite of what you'd normally do, right? When would you do this right here, this first example? When you're doing some calculations and you don't want to work with the giga in there, or the 10 to the, what is giga? Kilo, mega, giga, 10 to the 9th. Very good. All right. So actually it might be easier to work with is 2 times 10 to the 9th, just like that. Okay, 0.25 mega ohms to ohms. 0.25, we would never do that, would we? 0.25. See, 0.25 is not in proper engineering notation, is it? Oh, 0.25 mega ohms, okay. That's, well, almost a trick question. 0.3 kV, 300 volts in other words. You'll get to the point where you'll look at these and you'll instantly analyze them without any further trouble. 808 kilohertz to hertz. Okay, 2.4. This is not how we usually do it. Normally we're going the other way, simplifying a big number or a small number into engineering notation. Solving electric circuits. Solving electronic circuits, if a problem gives the measurements in units other than Ohm's law, series circuits, parallel circuits, and power, we must change all measurements to amperes, volts, ohms before we can use any of these formulas. Okay, what is this? Find voltage that will force 28.6 microamps. So that's really 0.0000286, right? Okay, of current through a 70 kilo ohm, so 70,000 ohm resistor in the base unit of a transistor. So once again, we're using engineering notation to simplify because we're going to turn this into powers of 10, right? And micro, that should have, 28.6, we're going to turn that into 28.6 times 10 to the minus 6. We're going to change 70,000 at 70 times 10 to the third. Find the voltage, E is equal to I times R. E is 28.6 times 10 to the minus 6 times 70 times. So then we can regroup this and get the numbers, the whole numbers together, and the powers of 10 together. Then it becomes a lot simpler. 28.6 times 7 times 10 to the minus 2. Or 200.2 times 10 to the minus 2, or 2 volts. 2.002 exactly, but who's arguing over 2/1000ths of a volt? Working with equation basic principles. Anything you do to one side of the equation, you got to do the other side of the equation. Anybody heard of that back in the 5th grade? Everybody heard that back in 5th grade, or 6th grade, or 4th grade, somewhere back there? Whatever you do to one side, you got to do that. Now, we're going to have a couple rules. I got to warn you. We have one special rule coming up. Okay, rule 1, the same number may be added to both sides of an equality without destroying the equality. If we add 1 or 2 or 3, we can add anything to either side, right? But generally, we're subtracting something from both sides to get rid of something, right? Okay, write the equation 3 times 4 is equal to 12. No, we shouldn't do that. That's too simple. Back to 3rd grade. Okay. Rule 2, the same number may be subtracted from both sides, which is what we actually do most of the time. Oh, not 3 times 4 again. Yeah, I can guarantee you that's from the book. Basic principle. Rule 3, both sides of equality sign may be multiplied or divided by the same number without destroying the equality. I didn't even think we got the divide by, but if you divide, by the way, I want to add one more, I forgot I should have put this in. I hope I watch this again before I present this PowerPoint presentation again. You realize what taking the reciprocal of something is? If you have 500, what is the reciprocal of 500? 1 over 500. You realize that if we take the reciprocal of both sides of something, it's okay? Same thing, it's like multiplying or dividing, or taking the reciprocal. But we're going to, that in the second semester, that becomes a very important rule because, well, you'll see. Okay, silly stuff. Do the arithmetic. Let's move on. And rule 4, both sides may be divided. Oh, they did have that one. Okay, let's rush through this one because everybody knows you can divide both sides by a single number. Okay, basic rule 5, to eliminate the number which is multiplied by the unknown letter, divided both sides to the equality sign by the number of the letter. What? Okay, solve the following equation. 2r is equal to 10. What happened here? R is equal to 5. What is this? 14 is equal to 7. Oh, that's a different question. Sorry. Okay. Kind of confused me for a minute. Okay, rule 6. To solve a simple equation in the form a number multiplied a letter equals a number, divide the number all alone on one side of the equality sign by the multiplier of the letter. An example of that would be 18 is equal to 0.3z. You want to find the value of z, so you want to get all the numbers on one side. So you're just going to divide, get the numbers on one side, get the letter by itself. But what happens when it's not that simple? Mr. Rogers' rule comes into play. That's what happens. To remove everything from one side of an equation, such as when you are trying to get just a number by itself, such as x sub l, or not a number, I shouldn't have number in there, I should say a variable like L. Now this is actually a formula from the second semester. X sub L, inductive reactance, is equal to 2 pi f times L, the inductance in Henry's. A completely foreign formula to you, right? But since you're brilliant, you don't need to remember all that stuff. You just need to get L all by itself, right? Because you're looking for L. Where XL is 20 ohms and F is 60 cycles a second. So we want to get L all by itself. So the reciprocal of 2 pi F is 1 over 2 pi F, right? So let's take that, and we have the old rule of X sub L was equal to 2 pi F L. So we're going to divide X sub L by 2 pi F L. And over here on the right, we have 2 pi F times L times 1 over 2 pi F. So the 2 pi F is going to drop out. I wonder if I can write on this thing right now. I don't know. We'll see. So this and this are going to drop out. Is that correct? Okay, and all we'll be left with is our L on the right side. So I created a reciprocal of everything was over there I wanted to get rid of. Okay? And there are going to be lots of times when you have this complex formula and you're trying to get this one thing that's on the right or on the left and you want to get it all by itself, create a reciprocal. Just flip it over and put everything that's on the one side that you want to get rid of and turn it into a reciprocal. Just flip it over. Oh, let me go back a second. Okay, and since everything in a number except L, so we can easily find 20 divided by 2 times 3.14 times 60 is equal to L. And that's a real calculation that you might have to do. Okay, another example, we have a complex formula, X sub C, the capacitive reactance, is 1 over 2 pi F C. And we want to find C. And this is something you'll need to find occasionally in the second semester. But the process of getting there is just using that reciprocal thing again. Since we know we're looking for C, and we have a number of X sub C, 12 ohms of capacitive reactance, And frequency is still 60 cycles a second. We're trying to find C, so we have 12 is equal to 1 over 2 pi, which is a number, right? 2 times pi is a number. Times 60, that's a number, and we want to get 60 all by itself. So what's the reciprocal of 1 over 2 pi f? What's the reciprocal of 1 over 2 pi f? 2 pi f. We multiply 1 over 2 pi f times 2 pi f. They cancel each other out, right? Okay. Uh-oh. So, I think that's what I just said. That's the reciprocal of it. So our formula becomes 12 is equal to 1 over 2 pi f times 60. C becomes 2 pi f times 12 is equal to just our C, because here again we can see that our 2 pi f, 1 over 2 pi f, 1 over 2 pi f, and our 2 pi f are going to drop out, and we'll be left with just 2 pi f times 12 is equal to 1 over C. Now here's that trick. I wound up with 1 over C on this side, right? Because 1 over 2 pi f times C, if I do the reciprocal thing, this is still 1 over C, right? Okay, so we have to leave that alone. But now I have this number, and this is a solid number, right? This is a real number. 2 pi, and we can turn that pi into a number. But we now have all the numbers on the right side, on the left side. Get this thing out of here for a second. And so we have 1 over 2 pi 60 times 12. Let's go back there just for a second. Uh-oh. Okay. So, I made a mistake here. Oh, I made this a reciprocal right here. You see it? This is 1 over 2 pi 60. And that whole thing times 12. You see what happened? We just took the reciprocal of this side.
I think the parentheses between 2 and 12 and not the.
I agree. I agree. Let's undo that. That should be between here and here, because we took the reciprocal of that whole thing. And 1 over is a reciprocal. So 1 over, so if we just take this number, this is a number. 2 times 3.14 times 60 times 12 will give us a number. And then if we have a handy-dandy TI-30X2S calculator, we can just hit x to minus 1, enter, and it'll tell us what that reciprocal is. And that is going to be a very small number over here, right? Okay. Let's go to the next thing. Estimating answers, I call that ballparking. Use the following procedure to estimate an answer. Change the measurement to proper units. Write out the problem. Convert the numbers to scientific notation, or engineering notation better yet, and solve the powers of 10 and the numbers. Estimate the numbers. So that when you start pushing numbers with your fingers on your calculator, when you get a number that's way off, you realize you've made a mistake. Because very often you'll make a mistake with your fingers that you don't realize that you made a mistake until it's too late. So you often want to ballpark a complex answer before you do anything else. Okay, a large launching rocket flew 0.0301 miles in 2.2 hours. Find the speed in feet per minute. They're converting factors here, right? I'm not a big fan of this little problem, but that's okay. Write the problem in scientific notation. Look only at the powers of 10 and get the numbers by them, the numbers together and the powers of 10 together, and it'll be easier to look at. The The answer is approximately 1.25 times 1, which is equal to 1.25 feet per second, or feet per minute, whatever it was. Okay.
Just come back another time.
All right. We have a little quiz on the things we were just doing. 2,500 times 10 to the minus third. We're going to simplify that to 25 times 10 to the third times 10 to the minus third. 10 to the third, 10 to the minus third are going to drop out. So we just have 25. Once again, it's a nice simple way. This is 0.0045 is going to be 0.45 times 10 to the minus third, right? Divided by 10 to the second, which is 10 to the minus 2. So we're going to have 10 to the minus 5, 4.5 times 45. I would have said 4 point, oh, whatever. That's what I would have said too. I think that's incorrect, but that's okay. 0.0005. What unit is that in engineering notation? This one right here. 0.0005. That's 50 times 10 to the minus 6th, right? It's a micro something times 0.003, which is milli, 10 to the minus 3. So we've got 10 to the minus 9th and 10 to the minus 3 plus 50 times 3. I bet that's 150 times 10 to the minus 9th is what I would have said, but 15 times 10 to the minus 8 will work out also. Okay, I'm not crazy about the little quizzies. And a bias voltage of 300 millivolts appears across a 2 mega ohm resistor. Find I. There won't be any current flow. It'll be too small to measure. That's what I know. That won't happen. You won't be able to measure that. Okay. End of slideshow. Click to exit. I think we'll stop there, and we're going to make this. There's another one coming up. We'll do that in just a few minutes. We'll take a break, but don't go away.